All right, I hope everybody's having a good day so far. I know I'm feeling a lot better. Had the bug last week. I know a few people are out sick, but it's good to see that most of you are here. Okay, so tonight what we're going to do is we're going to put some application to parallel circuit analysis. If you actually look at the lecture notes that are posted online for week 6, which this is the first part of week 6, it's entitled Parallel Circuits. Now, as everybody knows, we have already had a rather thorough introduction to parallel circuits. And so what we're going to do tonight is we're going to do analysis. We're going to solve problems, and I'm going to give you examples that are going to be very similar to the types of problems that you're going to see on future quizzes and also on the midterm and the final. Okay? So we're just going to jump right into solving parallel circuit problems. What we'll do, though, to start out with, though, is we'll talk about total parallel resistance. Okay, well, we've seen this before, but since we're going to be using it in our analysis tonight, I'll just do a very quick review of it. Let's just say that hypothetically we had 3 resistors, R sub 1, R sub 2, and R sub 3, and they were all in parallel with each other. And what we wanted to do is we wanted to find one resistor that would represent the same effect as all 3 of the resistors on top. So we want to find the equivalent parallel circuit. Well, we could label that as R1, 2, 3, which would tell us that we are basically integrating the effects of resistor 1, resistor 2, and resistor 3 all in parallel in this one resistor. Okay? Our book likes to use the notation R total. Okay, so we can call it by either name. It doesn't really matter. But we're really talking about the same thing. And as we have seen, the general formula for total resistance of parallel circuits is simply equal to the inverse of the sum of the inverses. So 1 over the inverse of R sub 1 plus the inverse of R sub 2 plus the inverse of R sub 3 plus the inverse of R sub n. And that, of course, just means that you can keep going and going and going. Okay? If you only had 3 resistors, then you'd stop right there. Okay, so what we're going to do tonight is we're going to use what we've learned in our previous exploration of parallel circuits in analyzing some circuits to just get some more practice, both for this class and also for upcoming industry aptitude exams. So let's say that we were given the following problem. Let's say we're given a problem where we have a battery. Let's say that the battery has a source voltage that's equal to 7 volts. Write that a little cleaner there. So that's 7 volts. And then this is hooked up to a parallel circuit. Start out with a simple one where R sub 1 is 100 ohms and R sub 2 is equal to 72 ohms. So that's what we're given. And let's say that what we're asked to find are the following. We're asked to find what the total current is that's flowing in the circuit. That would be the current that's leaving the source. We're also asked to find what the current is that's flowing in resistor number 1. We're also asked to find what the current is that's flowing in resistor number 2. also asked to find what the power dissipation is in resistor number 1. And finally, the power dissipation in resistor number 2. And that'll be plenty for right now. Okay, now, several different ways to solve this circuit. Okay, there's not only one way to do it. And we don't always have to start with the first thing that we're asked. Okay? In other words, we don't necessarily have to go from left to right as long as we get everything. Okay? Now, as I look at this circuit, one of the things that jumps out at me is the fact that I have two loads connected in parallel. And if I look at these loops right here, there's only two things in each one of the loops. Right? So by inspection, what's the voltage drop across resistor number 2, resistor number 1?
Same as the 7.
Yeah, it's the 7 volts. Okay? So I know this is 7 volts right here. Okay? Because Kirchhoff's voltage law, I know that the sum of the voltages around any closed loop has to be equal to 0, or, said more plainly, this voltage has to be the same as this voltage. So if this is 7 volts, this is 7 volts. If this is a closed loop right here, then this voltage has to be the same as this voltage. So in other words, everything's 7 volts. Okay? Well, if I know that there's 7 volts across here and I know the resistance, then I can very easily calculate the current. Because I know that by Ohm's law, I know that current is equal to voltage divided by resistance, don't I? That's one of the formulas in Ohm's law. So if I know the voltage and I know the resistance, I can immediately find the current that's flowing there. So that would be the current flowing through resistor number 1. Okay? And if I plug the numbers in, that would be simply 7 volts divided by 100 ohms. What do you get when you take 7 divided by 100? 0.07? 0.07. So the current is equal to 0.07 amps. So basically, I've just found that. Okay? Likewise, I can do the same thing here. If I know that this is a closed loop and that this has 7 volts across it, then this has to have 7 volts across it. So the current that's flowing in resistor number 2 has got to be equal to the voltage across the resistor, which is 7 volts, divided by the resistance, which is 72 ohms. So what does that come out to? 0.097 amps. So I've just figured out that guy. Okay? Now, if I want to figure out what the total current is next, okay, what law do you think I would apply that would allow me to find that most easily, knowing this current and this current?
Sum of the two branches.
Sum of the two branches, which is which law? Kirchhoff's current law. Right? Okay? So, by Kirchhoff's current law, it tells me that the total current is equal to the current in resistor 1 plus the current in resistor 2. Current in resistor 1 is 0.07. So that's equal to 0.07 amps plus the current in resistor 2, 0.097. 0.097 amps. So when I add 0.7 to 0.097, what do I get?
0.097.
0.167 amps. So now I figured out the total resistance. Okay? So I've captured this guy, I've captured this guy, and I've captured this guy. Now, to figure out the power that's dissipated by each one of these resistors, I go to my Ohm's law wheel, okay? And one of the formulas that I find in my Ohm's law wheel is a formula that says power is equal to current squared times resistance. Well, if I know what the resistance is and I know what the current is flowing through the resistor, then I can figure out how much power is being dissipated as heat in watts. So the power that's dissipated in resistor number 1 is going to be equal to the current that's flowing in resistor number 1, quantity squared, multiplied by resistor 1. And that's simply going to be equal to 0.07 amps quantity squared multiplied by 100 ohms. 100 ohms. So what do I get for that? 0.49 watts. So now I've just figured out what that is. And then likewise, the power that would be dissipated in resistor number 2 would be equal to the current in resistor number 2, which is 0.097 quantity squared multiplied by the resistance of resistor number 2, which is 72 ohms. So what do I get with 0.097 squared times 72? 0.679 watts. So now I've figured out the last thing I was asked for. Okay. Now, that's one way that we could solve that circuit. Okay? Another way that we could solve that circuit, can anybody tell me what another way we can solve that circuit would be?
Solve it for what?
For everything.
For everything.
Yeah, just another approach.
Well, you can find out RT first.
Exactly. That's what I was looking for exactly. Another way that we could do it, I'll move over here to the right a little bit, and I'll cut the board, a little jagged line. Another approach would be for me to redraw the source, which is 7 volts, and find one resistor that would be our total. Now, obviously the formula that I would use to find R total would be that formula that says R total for parallel circuits is 1 over the inverse of R1 plus the inverse of R2. And if I did that, let's do that, R total would be equal to the inverse of 1 over 100 plus 1 over 72. So what do I get for R total? 41.86?
That's what I got.
41.86 ohms. So this guy would be 41.86 ohms. Now, if that total resistance is 41.86, could I use that equivalent circuit to figure out what the total current is that's flowing from the battery?
I equals V over R.
Right. current is equal to the ratio of voltage divided by resistance. And in our case, this is going to be source voltage divided by total resistance. So that's going to be 7 volts divided by 41.86 ohms. So what do you get when you calculate that? 7 divided by 41.86. What do you get? 167. 0.167 amps. So if you notice, I'll change colors here for a second. If you notice, this number right here is the same as this number right here. Okay? So regardless of which method we use, we're going to get the same answer. Now obviously, if we would have decided to solve the circuit using this approach, okay, then what we would have done is we would have found this first. This would have been the first thing we found. Okay, the approach that I used when I first solved it was to first find this current, then find this current, right? And then by adding these two currents together, then I find my 0.167 amps. Okay, so it doesn't really matter whether you do it this way using Kirchhoff's current law and Kirchhoff's voltage law, or you do it this way where you're using the formula for the total equivalent resistance. You're still going to get the same answers. Okay? Now if you ask the question, okay, but wait a minute. If I did it this way, I've redrawn the circuit, I've found the total current that's flowing to my total equivalent resistance, then how do I find all the other stuff that you asked for? Well, the key to that is that whenever you draw an equivalent circuit, you leave the circuit that you started with alone. You don't erase it. Because if you erase it, then you can't go back and use it. Okay, so that's one of the tricks in analyzing these circuits. If I had gone and found the total equivalent, or the total amperage being drawn by the total resistance of the circuit, then I would know what this is. This would be the first thing that I would find out right here. And then using this current right here, I could use Kirchhoff's current law in combination with the current divider to find the current in either one of the other two branches, and then subsequently the power. Okay, so you can see that obviously there's usually at least 2 or 3 and sometimes 6 or 7 ways to do the same problem. The reason that it doesn't matter which way you do it is because this all fits the scientific method, meaning that you're always going to get the same answer as long as you're using the right theorem or the right principle. Okay? Let's try another one. Any questions about this? Okay. Let's practice for a moment with the 3 different forms of the formula for finding equivalent parallel resistance. The first one I wrote down when we began, and that was that R total is equal to the inverse of 1 over R sub 1 plus 1 over R sub 2, and so on. The second one is what we call the product over the sum. Okay? And that guy is R1 multiplied by R2 divided by R1 plus R2. And we call that product over sum. And that's only good for two resistors, right? Okay. And then the other special case is a case where RT is equal to R over N. And who can tell me what case that applies to? Right. If you have a bunch of parallel resistors and they're all the same value. Okay? So let's go ahead and test the first top two. Let's say that we had a resistor, we had two resistors. And somebody pick a value for resistor 1. Just pick a number. 50. Pick a value for resistor 2. 100. Okay? And then what we're going to do is we're going to use both of these formulas to see if we get the same answer. Okay? So if we use the first formula, then we find that R1, comma 2, which is the same thing as R total, is equal to the inverse of 1 over resistor 1, which is 50 ohms, plus 1 over resistor 2, which is 100 ohms. So what do you get when you calculate this? 33.33 ohms. Anybody else get that? Okay. And obviously that would be a situation where we had just one resistor, and that resistor was R total. But it has the same electrical effect. Okay? It offers the same opposition to current flow. Now, for the second test, let's test the product over sum formula. So R1, comma 2, which is equal to R total, should also be equal to the product over the sum. The product is 50 ohms times 100 ohms divided by the sum, which is 50 ohms plus 100 ohms. So I'll just make a bracket like that, which distributes the unit. So what do you get when you go 50 plus 100, invert that, multiply by 100, multiply by 50 equals 33.33. 33.33 ohms. So you can see that either one of the two approaches gives you exactly the same answer. And the reason is because they're mathematically the same. Okay? Let's talk a little bit about something that we've talked about in the past, but is important enough to mention again. Let's say that we're given the following circuit. And let's say this is resistor 1, this is resistor 2, and they're both equal to 100 ohms. So in this case, we've got two parallel loads, resistor 1 and resistor 2, both equal to 100 ohms. but we have two active sources that are connected in series with each other. Okay? Now, what is the first thing that you would do if you were asked to find what the total current was in the circuit? In other words, what is this current right here?
R over N.
Okay, that could certainly be the first thing that you could do. In other words, if you wanted to combine these two resistors into one resistor, okay, and for sake of room on the board, I'll go ahead and erase and combine these into one resistor. So if I combine this into one resistor, I'd call it R1, comma 2, which is the same thing as R total, which would be equal to R over N, which is the same thing as 100 over 2, which is the same thing as 50 ohms, right? Okay, now what's the next thing that I have to do?
Voltage over resistance.
R equals I equals U over R.
Okay, so when I take a look at these two voltage sources, is there a way I can simplify these? Yeah, I can just add them together. And the reason that I can just add them together is because of the polarity. And that's what I want to emphasize here. Okay? There's two ways that this circuit can go. It can either bump the voltage up to double of what either one of the individual voltage sources are or batteries are, or it can cancel it out so that you have no electrical pressure. Okay? Now, with the way that I've drawn it here, okay, I could redraw this voltage source so that it was one voltage source with a magnitude of how many volts? 28 volts, okay? If, however, the polarity was changed so that instead of this being plus minus, it was minus plus, then I would have 0 volts. Why? Because they're working against each other. The two batteries are working against each other. Okay? But I just wanted to show you that as an example. So generally you're going to have the batteries polarity so that they're working to aid each other. It's called polarity aiding instead of polarity opposing. So I could simply take these two batteries and substitute one single battery, and this would be 28, right? 28 volts. And then if I wanted to find the current, what law am I going to use now? Ohm's law. Right. We've seen this many times. Current is equal to voltage divided by resistance. We're talking about the total voltage. So if there's multiple batteries, we've got to basically break those down into one equivalent electrical pressure or one equivalent electrostatic potential difference, okay? Or one equivalent battery. And in this case, ours is 28 volts. And then our total resistance was 50 ohms. And so our current is going to be 28 volts divided by 50 ohms, which is equal to what? 0.56 amps. So this current right here is 0.56 amps. Any questions about that? Okay, now let me show you another type of problem that is very typical on industry aptitude exams as well as college exams that looks kind of difficult when you see it the first time, where it looks a little confusing, but really isn't all that tough. Yes? Pardon? Oh. Was blue not coming out that good? Okay. All right, we have to cut that whole part out, huh? Okay. All right, so what I'm going to do now is I'm going to show you a particular problem that is very common in industry aptitude exams as well as exams that you'll see in here. And it just looks a little funny when you first see it. But this is what it is. You'll have a battery, and then hooked up to that battery, you'll have another battery, and then hook up to that battery, you'll have another battery, and then hooked up to that battery, you'll have another battery, and then hooked up to that battery, you'll have another battery, and then you'll have another battery. And then you'll have a load, and then that load will come back to close the loop at your first battery. So let's just say that this guy was 4 volts, this guy was 2 volts, this guy was 9 volts, this guy was 2 volts, 4 volts, 8 volts, and the resistance was equal to 10 ohms. And the only thing that I want to know is how much current is flowing through that load right there. Now, what's the first thing that you're going to do to solve this problem or to simplify this problem? Right. What you want to do is you want to add up the voltages, but you need to be real careful when you add them up, because if you get the polarity switched around, you might be having 2 of them cancel each other out when in fact you should be doubling them. Okay? So let me show you the approach that I use. The approach that I use is to take my batteries and count them. I count how many sources of electrical pressure I have. I have 1 battery, 2 batteries, 3, 4, 5, 6. I have 6 batteries. So what I do is I rewrite the batteries like this. 1, 2, 3, 4, 5, 6. Okay? So I write my 6 batteries like that. And then ultimately what I'm going to do is I'm going to take a lead off of the top battery, and I'm going to bring it down parallel like this, and I'm going to put my resistor right there, and then take it down to the bottom battery. Now, I've changed the topology of the circuit, in other ways the way it's drawn, but I haven't changed anything electrically about the circuit. What I can do now is I can go through and I can figure out whether or not batteries are canceling each other out or they're adding each other. They're aiding each other. So if I start out with this as my first battery, okay, then let's say that this battery right here is the battery that is on the bottom. So this guy here is going to be my 4-volt battery, okay? And it's going to have a polarity that points positive on the top and negative on the bottom. Because you notice here that this negative terminal is connected over to the load. Follow over to the load. Okay? So then what I'm going to do is I'm going to follow this positive terminal, which is the point where I am right now, this positive terminal, and I'm going to follow it over to my next battery, and I'm going to see what polarity I come into. Is it negative or positive? It's negative. So I'm going to draw a straight line up to this point right here and then put a negative. And then I'm going to obviously put a positive at the top. So now my positive goes from the second battery over to the third battery, and it comes into a negative. So this guy goes straight up and into a negative. And then obviously the opposite side has to be positive. So I come out of the positive, and then I follow it over, and it goes into a negative. So this is going straight into a negative. And then obviously that has to be positive. So then this positive goes into a positive. So I have to come out of here, come straight up, and into a positive. And then obviously the top has to be the opposite, which is negative. And then my negative comes over and goes into another negative. So my negative goes straight up into another negative. Okay? So now I can draw my polarities. So I've got 4 volts, I've got 2 volts, I've got 9 volts, I've got 2 volts, I've got 4 volts, and then finally I've got 8 volts. Okay, now, one of the things that makes it a lot simpler when it's all drawn vertically like this is I can figure out which batteries are aiding to the electrical pressure and which ones are taking away from the electrical pressure. Okay? So if I look at the batteries that have a positive terminal on the top, okay, then what we're going to do is we're going to add those voltages together. So if I take this one, it's got a positive on the top. I'll put a check mark by it. So there's 4 volts. Here's a positive on the top. There's 2 volts. Here's a positive on the top. There's 9 volts. Here's a positive on the top. There's 2 volts. And then I got another positive on the top up here, which is 8 volts. Okay? And then the only thing that's left over is this battery right here. Okay? That battery has a polarity that's opposite all the others. And so I'm going to add all of these together. Somebody want to do that for me? 4 plus 2 plus 9 plus 2 plus 8. What is that? So that's 25 volts. And then I'm going to have to subtract 4 volts, which is going to give me 21 volts. So what I can do then, to further simplify the circuit, is I can erase all these batteries right here. And I can replace them with one single battery that has a polarity positive to negative that is 21 volts and 10 ohms. And the point of that circuit was to show you how you can take batteries that are kind of all mixed and gumbled and thrown into a bag, so to speak, and boil it down into one battery that will give you the electrical pressure you'd have if you set that up in the lab. Okay, let's take a look at one more example. Were there any questions about that one?
Yeah, what is I?
I'm sorry? Oh, thank you. Thank you. I found everything except what I was looking for. Okay. So the current that's flowing through my load is going to be the same in this circuit as it was in that long string of batteries, right? Okay? So the current that's flowing through the load is going to be found using Ohm's law, right? So current is equal to the ratio of voltage divided by resistance. So this is going to be truly the total voltage, because we had a whole bunch of different voltage sources. So we basically found the total voltage, and then we're dividing that by the total resistance, and obviously that's equal to 21 volts divided by 10 ohms. And what do you get when you take 21 volts and divide it by 10 ohms? You get 2.1 amps. Okay? Okay. Thank you for not letting me get away with not finishing the problem. Are we beeping? Okay. One more example. And what I'd like you to do is I would like you to get out a piece of paper and your calculator, and I want you to see if you can figure out this problem. Okay? Check for understanding. This is what you're given. Okay, this is what I want you to, this is what you're given. You're given a circuit that has 2 batteries and 1 resistor. Everything's in parallel. The batteries are both 12 volt. They're both 12 volt batteries, but they're independent batteries, totally separate from each other. Okay, this is what I want you to find. I want you to find the voltage across the resistor. If you were to hook up a voltmeter over here, let's say this is a voltmeter, and you were to take this voltmeter and hook it up right here and right here, what reading would you get on that voltmeter? That's the first part of the question. The second part of the question is, how much power would you dissipate in resistor 1 in watts? So we'll give just a couple of minutes for everybody to try to work it out. Okay, so let's come back to our check for understanding here. We had 2 12-volt batteries that were in parallel, connected up to one load, which is 50 ohms. Let's talk about the voltage that we would measure here, because this is really important. A lot of folks get this wrong, and there's no need to get it wrong. Okay, if you get it wrong this time, you know, this is the place to make the mistake. The place not to make the mistake is on the aptitude test for PG&E or Chevron or, you know, whatever big company you're going to work for. Okay. What am I going to read on the meter? Okay, why not 24?
Because they're in parallel.
Because they're in parallel. Very good. Very good. When you hook up 2 batteries in parallel with each other, and those of you that have ever done this with an automobile or something, right, you don't get 24 volts. You still have 12 volts, right? And if you use Kirchhoff's voltage law, this is a closed loop right here. The sum of the voltages around any closed loop has to be equal to 0. Or, in a more simplistic way, we can say the voltage here has to be the same as the voltage here. And we look at this and we see that this is 12 volts, this is 12 volts, so it meets Kirchhoff's voltage law. Okay? If we come over to this closed loop right here, again, the sum of the voltages around this closed loop has to be equal to 0, or, said more plainly, this voltage must be equal to this voltage. So, yes, 12 volts. So this is going to be 12 volts. Now, what about the power that's being dissipated on this resistor right here?
We got 2.88 watts.
Okay, what formula did you use?
We used E over R.
E over R for power?
No, E over R equals I. And
Okay.
I times E.
Okay, all right. Well, I know a lot of us did it different, but let's try this. How about power equals voltage squared divided by resistance?
You could do it that way.
Okay? All right, so let's take our voltage, 12 volts, and let's square that quantity, and let's divide that by 50 ohms. What do you get for power? 2.8. 2.88 watts. Okay, now, very important. If I were to take another battery and add it to this circuit, the polarity is the same as the polarity of this battery, and the voltage magnitude is the same, 12 volts. The question is, will my power dissipation change here? Will it go up? No. I could add 1,000,000 batteries that are 12 volts. What is it that these batteries do for me?
More current.
They give the potential to deliver more current if I need it.
And they also run each other down.
And they do also run each other down. Okay? All right. Any questions? That's good. Most folks get that one wrong. Question?
So basically, it doesn't matter how many batteries you have, you're going to get 12 volts, but just backup current or something like that.
Yeah. Like, for instance, let's say that you're going to be going to Alaska. You go snowboarding in Alaska, and you got, a truck. And it's going to be cold. It's going to be 40 degrees below zero. And you want to make sure that that starter motor turns over, right? I'm probably going to put 4 truck-sized batteries all in parallel with each other, right? Because when I turn the key for the starter motor to turn over, all 4 batteries are going to be pumping current if it needs to draw that much current. So if the cold cranking amp requirement is, let's say, 2,000 amps, then I'm going to have it if I got 4 batteries, right? If I only have 1 battery, I might only have 800 cold cranking amps. That make sense? Okay. If you have anything else, come on up and see me. Otherwise, drive safely. Have a good night.